Hi. So the objective of this project is to predict the energy efficiency of a combined cycle power plant. And this is a kind of power plant which uses a combination of gas turbines, steam engines, and other heat recovery steam generators to increase in a sort of a multi-stage process uh, to derive maximum efficiency out of the electricity generation process. Uh, to create this model, we have roughly 9.5K hourly average ambient environmental readings. These are coming from sensors within the power plant, and some of the features that we have here are temperature, ambient pressure, relative humidity, exhaust vacuum. Uh, the output variable here is net hourly electrical energy output, and this is exactly the variable that we are trying to predict from our model. To start our modeling process, what we initially do is go through some online articles and try to understand the process a bit better. Try to understand what input factors might or might not impact the efficiency of uh, the whole process, essentially, the uh, quantity of electricity produced from the whole process. So typically what we noticed is a normal power plant, while might have somewhere around a 45% efficiency, since this is a multi-stage process, efficiencies go upward of 65-70%. And this efficiency is largely dependent on the ambient pressure. Uh, the solid bullets that we are seeing here are exact statements that have been pulled out from our external source. We have used Wikipedia as our source here, and the sub bullets are the conclusions that we have derived out of it. So, all in all, just to summarize it, it feels like from this particular article that low ambient temperatures promote high efficiency, and as temperatures get hotter, efficiency would be lower. The same thing can be said about pressure. There might be some interaction term based on my reading of the article. There might be some interaction term between ambient pressure and the pressure at the exhaust vacuum, and the difference between the two pressure points is something that might impact the efficiency of the whole process. So if the power plant is in a place where the ambient pressure is uh, there's a high delta between the ambient pressure and the exhaust vacuum pressure, it might lead to a higher efficiency. Now, some baseline setting for our modeling and analysis. The total number of observation counts are 9568, out of which I have pulled out 10% data, which is roughly 970 uh, for the test set. Our training data count is 8598. The validation mechanism we have used is a four-fold cross validation. So essentially, we are dividing this 8598 into four parts, and that gives us 1719 uh, observations for every validation set. One more thing I noticed is that both V and AP are measure of pressure. However, the units are different as has been provided in the data that I have. I have used this conversion. 1 centimeter Hg is equal to 13.33 roughly millibar. I've utilized this number to make sure that both of them are in the same unit when I'm calculating any interaction term within the two. Now, to evaluate our various mechanisms for analysis, we can use Excel, we can go for a programming language like Python, or we can use one of the online AI tools like ChatGPT for doing this analysis. Each has their pro and con. However, given the size of the data that we have, which is relatively small, um, it makes sense to go for Excel because it's relatively simple. Not a lot of coding is required there. It also has an inbuilt regression modeling tool. Uh, while Chat GPT might be easy, but it does not give us a lot of insight into the process of the modeling. So we want to be able to fine tune and tweak some of these parameters, coefficient hyperparameters, and It's not as easy in ChatGPT as in Excel. Python gives us a lot of flexibility. It's very difficult to test out these models. Sorry, it's very uh, uh, versatile, and it has a lot of libraries that can easily help us get conclusion out of these models. However, it requires some programming knowledge, uh, and it can get too difficult too fast, depending upon the type of analysis that we want to do. One advantage of Python is that we can, like, while Excel provides us only with a regression tool, with Python we have libraries to test some of the other uh, more sophisticated algorithms. However, in this particular case, given the type of data as well as the size of data that we have, uh, it makes sense to use an Excel, which provides a fair balance of control as well as accuracy. Um, we also took into consideration I also took into consideration a bunch of other parameters, like the computational resources required and the input output relation and things like that. But uh, essentially, I mean, we can go through each one of them, but all in all, the conclusion is that an Excel based regression would seem like an appropriate choice for this particular use case. Now, to go into the evaluation process, we look at the data that we have. So we have 9,568 data points excluding the header row, and we have divided this into a training set of 8,598 and a test set of 970 data points here in the Excel. And further, we have subdivided this whole data set into, for each of the iterations of our cross validation, the four stage cross validation, we have divided it into three parts of training data, which is 6,879 observations, and one part of validation data, which is 1,719 data points. Now, once we divided this into training and validation sets, for each of these training sets, what we did was run the regression model for the various models, run regression for the various models, and I'll get to the models in a moment. And once we got the outputs of those models, we use that on our validation set to calculate our output metric and see how it is performing overall. So yeah, let's get back to the data. All right. So the first step, even before we start modeling, is to prepare the data, as I walked everyone through that right away. But after that, we want to understand what does our data tell us. And the first step to it is to understand if there is some interaction or correlation. I wouldn't say interaction, more like if there's some correlation between some of the features that is present in our model. So basically, what I'm trying to say here is if one of the input features impacts the output as well as another input feature, in that case, instead of using both of those input features, we can just get rid of one of them to make our model simpler. That's what I'm trying to calculate here with the correlation logic here. And what we are seeing here with this particular table is, now obviously 80 to 80 interaction will always, the correlation will always be 1 with itself. However, we see that there's a high correlation, high positive correlation between V and 80. For the other features, it's not as high. It's roughly like in the 30 to 50 range. This is like 84 is 0.84 is like a really high correlation number. So our conclusion here is that probably we should try out a model where we use one of these two features instead of having both of them. and see like if how it impacts the output. The second thing we did was trying to identify the output correlation with input, and P is our output variable, AT, V, AP, RH are all our input features. From our reading in Wikipedia earlier, we found that there might be an interaction term at play here, which is the difference between the ambient pressure and the exhaust vacuum. So that is another term that we experimented with at this particular stage to see what sort of correlation are we getting out of it. Uh, a high positive or a high negative correlation might indicate that that particular feature can prove important for our modeling purpose. And that's what we see here. AT and V have a strong negative correlation. Uh, the interaction term between AP minus V has a strong positive correlation. So again, something to keep in mind while we are designing our models, while we are selecting input features for our models. Another thing that we do is do a graphical analysis, and here I have plotted each of the input features against the output variable to visually see if I can identify any non-linearity in the relationship between the two. So while AP versus PE and RH versus PE, I'll just zoom in here. AP versus PE and RH versus PE, these two graphs seems to be more of a scattered plot. I do not see any defined correlation, like very strong conclusion that I can derive out of it. However, for the first one, AT versus PE, there's clearly a very strong negative correlation. V versus PE also, I can definitely say there's some sort of a negative correlation happening here. It's not exactly very clear if it's linear or there's some non-linearity in it. However, when we look at the AP minus V, the interaction term, we clearly can see some sort of a non-linearity happening here. The curve doesn't look like the curve is a straight line, absolutely straight line. So what this tells us that we might have to experiment with some non-linearity for this particular input feature. Based on all our findings, what we next do is build out a hypothesis for our models. So model 1, this is just for baseline setting to identify like what's the benchmark that we are getting with by taking all of our input features, running the regression on it against our output, and seeing what sort of a baseline value we are getting. So model 1 is more for baseline setting. Model 2, here instead of taking AP and V separately, we take the interaction term between the two. Our objective here is to see if each of these consecutive models, if each of these subsequent models has a higher explainability as compared to the first model, and by how much. Model 3, we experiment with the non-linear term AP minus V. We saw some non-linearity up here, so we are trying to see if we add a non-linearity here, like does that help our model better. Now model 4, what we are doing here is we are considering AP, ambient pressure, as linear and the interaction term as a non-linear term. And the reason for this is because while AP minus V, so there are various stages within a power plant for this whole power generation process, and while AP minus V might impact one of the stages where the exhaust vacuum happens. However, the ambient pressure might impact the efficiency of some of the other stages of the process. So that was one of the hypotheses that I had in my mind, and to test that, I created this particular model, model 4, and we will see how that performed with the other models. And finally, we have model 5. where we take each and every linear or non-linear term that we have experimented with so far to see if we are seeing any improvement in our model, if we utilize all our features and all their interactions, linear and non-linear and everything. So yeah, I mean, there is the next step here is to decide what metric we are using for our model selection. Now we have a couple of options here: the mean absolute error term, the mean squared error term, the root mean square error, and MAP term. While MAP is a good term for from business perspective, communicating the output efficiency in more of a percentage term. Um, for day-to-day processing as well as error evaluation, the first three terms are much better. Now, for deciding what output metric we want to use among these three, uh, we we run the model against one of our validation sets and try to see if we have a lot of outliers. Now, the plot that you see here is the predicted versus actual output for one of the validations. And what we notice here is that there is a presence of a lot of high um, high absolute value error terms, both on the positive and the negative side. So it tells us that our model will result in some uh, high outliers. And while mean absolute error might be good at sort of evening out the impact from these high value outliers, the mean squared error, on the other hand, will penalize these outliers more than it penalizes some of the low error quantum outliers. So, and root mean square error is just a square root version of the mean squared error term. Now, root mean square error is, in my opinion, relatively much better and more interpretable because its unit is same as our output metric, whereas the mean squared error will be a squared value of that particular unit. So, given these two, my choice would definitely be RMSE. However, for this particular case, um, I keep MAPE as one of the terms that I would use for business meetings and for showing the output efficiency to people in the leadership or things like that. Um, However, since the power plant is a sensitive place and high value of outliers can lead to a devastating effect, often leading to the loss of lives, uh, I would go for RMSE as the output metric. However, for this particular exercise, I have calculated both of these terms to see how our model is performing for each of these cases. Next, we look at the modeling results. As I showed earlier, what I have done is run four cross validation sets. For each of these cross validation sets, I've gone ahead and run the regression model for model 1, 2, 3, 4, and 5. And I've looked at all their outputs. And then I have drawn this table where I've summarized all my findings for the output metric for each of these models. What we can clearly see from here is model 4 and 5 are definitely performing significantly better than the other three models. Model 3 lies somewhere as sort of a middle ground compromise between the two sets. Our primary metric RMSE, we see there is a jump in there's a jump in improvement essentially in the metric that we are seeing between the first two and the third one, and then again a jump towards the fourth one. Fourth and fifth are roughly equivalent. We see that for other metrics as well. Now, based on this, the choice seems to be clear between model 4 and model 5. To decide which of these two we want to go for, we look at the model 5 regression analysis data, and what we notice here is that we might be overfitting this model. There is a probability in this particular model we might be overfitting, and some of our data in fact even has a zero coefficient, so we don't even need to have this particular input feature for calculating our output, which is the v value, given the other features that we have utilized for this. Some of the coefficients are extremely low, so this might become an overly complicated model. Uh, for this purpose, since the data is small, it's not too complicated from a computational perspective, but we need to think about how this data is going to be utilized in a particular power plant. When people are looking at this particular data point, going through the readings, they might need to tweak or slightly adjust the various elements or the various stages of the whole process. And having just having these many features with so much interaction between them makes it ever so complicated. Given that information, my recommendation would be to go for model 4, which provides a fairly high accuracy uh, among the models that we have tested. However, depending upon the tolerance of the whole system, model 3 would also not be a very bad model to pick. The gains we are getting between model 3 and model 4, while decent, uh, it's more of a business call what we want to go for between the two. For this particular case, I feel that for model 5, the gains we were getting were not justified versus the complexity we were introducing in model 5, so which is why I've gone for model 4. But between model 3 and model 4, it will be more of a business decision on what we can live with in terms of the tolerance. So yeah, there we go. Like, that's our formula for model 4, and this is the MAP number. Finally, what we do is take this particular model and run this on our test data. So we go to the last tab here, we calculate all our interaction metrics, and we use the formula to calculate our predicted value, the error, and uh, our output metrics. And what we notice is that our output metrics are roughly in the same ballpark as we had seen during our modeling process. The MAE number is slightly higher, I would say. Yeah, it's slightly higher than what we saw here during our validation. But yeah, our primary metric, which is RMSE, is perfectly in line with our expectation, in fact, slightly lower, as well as the MAPE metric. So that gives us fair confidence that the model that we have built will perform well in real world testing scenario, in real world scenario. Uh, yeah, that's about it. And thank you for being with me throughout this walkthrough.